Also with wireline, we've got the idea of the cross-dipole sonic that gives us both a fast and a slow shear wave shown in this track, and wherever they separate, we got this orange color. So the physics of this, the idea of this is that if you have a set of vertical fractures and you put in an arbitrarily polarized wave, it will split into two parts. One part perpendicular to the fracture plane that's slow, another part that's fast. And this blue line represents the average azimuth of the fast direction, and if you look down here you see the fast direction is parallel to fractures, and I've thrown a compass on here. So in map view, this well log indicates fractures along this orientation. So the well logs give us information about fractures and the fracture orientation, and also the separation here is a measure of fracture intensity. How fractured is the rock? So let's talk about horizons in the data. So this is an example taken from Osage County, Oklahoma, where we have tracked a middle Mississippian event, and we see on here a topography which is shown in the sort of geometry of this shape, the shape of it, but overlaid on that surface is the amplitude of that horizon. And what we see are valleys coming off a high ground. Now this is current day structure, so it has not been corrected for structural deformation after deposition, but the amplitude would not be affected by that, but the structure may well be deformed beyond the original depositional surface. But the important thing is here that we have amplitude anomalies running right down these channels. And the idea is that these areas blue represent hard consolidated limestone, and inside between these highs we've got these valleys of sediment which has been transported down the valley. We have enriched porosity, which means lower velocity, lower density, and gives us a reflectivity boost. And comparing that to the Bahama platform case, we feel confident that these channel feeders we're seeing here are in fact parallels to this modern analog of channels on the Bahama platform. The scale is similar, the geometry is similar, and in fact I can tell you that in the outcrop 100 miles away from this survey we have found two outcrops so far that transect these feeder channels, and we've actually seen it in outcrop. And it's a crinoidal debris flow that it clearly has flow indicators in the geometry of those small beds. Just a little mini case history here from Oklahoma. This is a student's work. Michael Kumbalik is just finishing up this semester. And over here is the stratigraphic column, and we see the Viola limestone, which is Ordovician in age. Got a survey down in this area. Here are the details on the survey. It's a pretty large survey, 180 square mile 3D. This data set was donated by Devon to the University of Arkansas for study. And if you look at the top of the horizon for the Viola, we see this picture on the left. Now this is actually similarity, coherence if you will, on a tracked horizon. We see lots of fault indications, large faults plus small splay faults, large faults, small splay faults. And this is an image from a recent paper talking about the way that carbonates fault and fracture. And there's sort of three regimes. We have, if it's an incompetent or poorly consolidated carbonate, you tend to get this kind of behavior. If it's a mixture, you get this kind of behavior, a few big faults with lots of splays off the side. And if it's a really competent rock, you get large block faults. So if you look at this, clearly the regime we're in here is right into the middle. And this study is taken from the Eagleford formation, not from the Viola, but it translates across to other carbonates. So the last little piece of our puzzle is seismic attributes. We've already seen a little bit of seismic attributes in the coherence, but there are other things that can be done as well. This is a screenshot from OpenDetect just to show how we can make a geobody in OpenDetect. There's a gas bright spot here in the North Sea. In this data set, you can see it in this very bright anomaly right in here. And we've picked one seed point here, and from that seed point we can set an amplitude threshold and grow a geobody so it will expand until it reaches that threshold limit and show us the geometry of this thing. And here it is. So here it is, just showing the limits of this. Now this is a gas bright spot. In carbonates, as it's been mentioned in your talk, we don't tend to have fluid bright spots because the carbonates are very dense, brittle rocks, and the fluid effects are minor. What we have in carbonates are lithology bright spots because we have unconformity surfaces. Sometimes we have development of fracture zones. Sometimes we have porosity development interior to the carbonate, and all of these lower the impedance and give us amplitude bright spots that represent desirable lithologies in the carbonate. But the methods of working with gas bright spots and lithology bright spots in carbonates is identical. The workflow is the same, but the meaning is completely different. So here it is, just hanging in space, just showing the geometry of that particular gas bright spot. And here it is relative to a time slice in the data. So now let's go back down to the carbonate section in northeast Oklahoma. And the top of the Mississippian is shown right here, and it's characterized by a subaerial unconformity surface. In places we have dense limestone against Pennsylvanian rocks above, and there's almost no reflection in that case. In other places we get altered rock at the interface at the top of the carbonate. Extra porosity, there's also a kind of a chert that develops in this area called tripolite, which is very low density, 2.1 grams per cubic centimeter, low velocity, gives you a very robust amplitude feature, which is shown over here. So that same technique for mapping the geobody that we just saw can be applied here. This is a zoom in of that effect. So here we are now with this horizon tracked, shown in purple here, and we can see where the amplitude anomaly sits, this tripolitic chert at the top of the limestone. And this tripolitic chert, by the way, is a very prolific producer when it's present. 40% porosity, great permeability, and it's a very desirable thing, but it's irregular in its distribution. You can see here that there are vast areas of this particular survey with no apparent tripolite, other areas that have it. So doing geobody extraction allows us to make these kinds of maps that show these are the places where this tripolite should occur, and if you wanted to drill and find out where you might make primary production, you can see that these are not all attached. There are some detached bodies in here. Some of the larger ones have been found by early drilling just on luck, but without 3D seismic and a systematic methodology, you would lose the ability to find the small ones. And even the small ones make very big oil reservoirs. Another way to look at this tripolite, rather than do a geobody, in this case we have flattened the data on this horizon right here, although it's not flattened here, but we did track this horizon, which is a sort of the lowest Pennsylvanian age horizon that we can track, and then we flatten on it and we slice through the top of the Mississippian and we see this picture. This shows us what this tripolite looks like in map view. We know of outcrops in northwest Arkansas with tripolite exposure, but you never can see it away from the outcrop, so we only have little snapshots of it. Here we can see it in map view. We know the size of it, the scale of a tripolite pod, you see 1 mile. Also the very delicate nature of it, where it is clearly related to replacement along permeability, high permeability zones in the rock. It's a secondary replacement of the original limestone.
What is a tripolite origin?
A tripolite is mineralogically, it is 99% silica. Silica.
Okay.
Up to 45% porosity. It is so there's a process that has taken limestone and leached out maybe 40% of the limestone to make very porous limestone. Then there's a second process that has come through and replaced all the remaining limestone with silica, so that you get a tripolitic chert inside the limestone. It's pretty rare worldwide, but this area is known to have it. We could talk about that a long time. So just to wrap this up, carbonates have a lot of very special characteristics. They are brittle, which means they're commonly faulted and fractured, which means that we can expect to have to do anisotropic imaging, either HTI or orthorhombic, in order to get it right. They are soluble, giving us complex porosity on all scales. That's very important. They're not VTI, like a shale is intrinsically VTI. Carbonates are not, but they'll be surrounded by clastics, including shale, so you'll probably have to do VTI processing. So you think about that, you've got to handle VTI anisotropy plus HTI or orthorhombic. So you just need to plan on doing anisotropic work in carbonates. They are also shallow. They are deposited in shallow water. They form in place, and that means that they are a delicate recorder of sea level changes and wave energy. When sea level changes by 30 meters, carbonates know it. They record it, where clastic systems often blow right through that. All right? But there are some deeper carbonates that form in deeper water, and those are very fine-grained lime muds, which can act as these vertical permeability barriers within the carbonate. On the point of being a sea level recorder, I'll just finish with this slide. This is from some work we've done in my shop. Here's a photograph of an outcrop in northwest Arkansas, and what we have is carbonate hard grounds with lime mud capping right here representing deeper water. So this is shallower water. It goes a little bit deeper and we get the lime mud, shallower again, and then a little bit deeper, we get the lime mud, and so forth. And these things, if you measure the height of these layers, you see what we have on the right, 6, 4, 2, 1. It is a thinning upward stacking pattern. And there's been a lot of work done by various people talking about stacking patterns and sea level curves. And this kind of a stacking pattern of carbonate, thicker at the bottom, thinning upward, represents a falling, a low stand of the sea level. So from looking at carbonate stacking patterns, you can actually say where you are on the sea level curve. And with that, I will just point out that our project at the University of Arkansas is called the Multiscale Arkansas Unconventionals Project, or markup. And this is how you can always get a hold of me. And this is a picture here of our Mississippian limestone on the Buffalo River, and this is one of the students fishing in the river. And with that, I will say, arigato.